Hi, I am Anrin, a PhD candidate at Stony Brook University, and today I'll be talking about SqORAM, a locality-preserving write-only Oblivious RAM. This is a joint work with my advisor, Radu Sayan. So this work is motivated by the need to protect sensitive information stored on local storage devices such as laptops, tablets, mobiles, etc. Now, as the first line of defense against adversarial attacks, we should always encrypt the data we store on these devices with full disk encryption tools such as BitLocker on Windows or dmcrypt on Linux-based systems. However, full disk encryption does not solve all the problems. This is because encryption does not hide access patterns. An adversary that can observe and snapshot a storage device multiple points in time can learn what locations on disk changed in between snapshots, how frequently a particular data item was updated, etc. As evidenced by a long line of work, access pattern leaks can completely undermine the protection of encryption. The main underlying reason behind this is that a lot of the algorithms that we use in our everyday applications have data-dependent access patterns. What this means is that the memory access patterns of these algorithms depend on the input data. A simple example here are sorting algorithms, but this problem also extends to more complex algorithms such as graph algorithms and machine learning. A common tool employed to hide access patterns from an untrusted storage adversary is a cryptographic primitive called Oblivious RAM or ORAM. Informally, an ORAM protocol allows an application to access items from an untrusted storage media without revealing to the storage adversary what items are being accessed and what operations are being performed. So Dilbert wants to access an item I from the untrusted storage, but instead of just reading the item I, Dilbert is going to employ an ORAM protocol. This may involve several rounds of communication where blocks of data would be read and written to the storage media. At the end of the protocol, Dilbert will be able to access the item that he wants, but what the storage adversary will observe is a bunch of uncorrelated read and write requests. ORAMs protect against full online adversaries that can observe all the reads and writes performed by a user. So they provide very strong security guarantees, and ideally, we would want to employ an Oblivious RAM to secure our local storage devices. However, ORAMs are also extremely slow. Deploying them to secure local storage devices is impractical because ORAMs would introduce prohibitive overheads for your I/O, resulting in unreasonably slow application throughputs. A crucial observation here is that local storage adversaries are usually not as powerful as online adversaries. Instead, most local storage adversaries have multi-snapshot capabilities. What this means is that the adversary can have arbitrarily many observations of the device. It can save disk snapshots and compare what has changed in between these snapshots. However, the adversary cannot observe runtime state, example, the contents of the DRAM, the file system caches, etc. And it cannot monitor runtime operations, example, syscalls. So in effect, what the adversary actually observes is the changes to the device due to writes and updates performed. Such adversaries are common in scenarios like plausible deniability and secure backup of data to untrusted remote servers. An application where multi-snapshot adversaries are common are plausibly deniable storage systems. Plausible deniability allows a user to claim that certain sensitive information is not in her possession even after she has been coerced to hand over her encryption keys. This is a key tool in the fight against censorship and oppressive regimes. There are several plausible deniability tools, which includes TrueCrypt and now its successor, VeraCrypt. TrueCrypt allows a user to create multiple logical volumes, some of which can be marked as hidden. The data in the hidden volumes are stored on the disk in the free space of the public volumes. So when the user is coerced to hand over her encryption keys, she hands over the key for her public volume and claims that the rest of the disk is free space. TrueCrypt then ensures that the adversary cannot distinguish between free space and hidden data, which is encrypted with semantic security. However, with multi-snapshot adversaries, TrueCrypt is insecure. This is because if some part of the hidden data changes in between snapshots, then this results in changes to the free space. If the free space is actually not storing any meaningful information, then it should not change usually. Also, real adversaries in plausible deniability scenarios usually have multi-snapshot capabilities. Example, these could be officers at border crossings in an oppressive regime that can snapshot your device every time you enter and leave the country. To protect against multi-snapshot adversaries, we do not require full ORAM protection. Instead, we can use a simpler and more efficient solution called a write-only ORAM. Now, as the name suggests, a write-only ORAM hides only the write access patterns. A simple way to build a write-only ORAM is to randomize the write access patterns. So for example, you want to store some data from a logical domain, example, a file system on the device. You use a write-only ORAM layer, and what this does is that it places the data from the logical layer at random locations on the device. Every time you update a particular data item, it is replaced to a new random location. So security-wise, the physical location of blocks on the device are random and therefore independent of their logical addresses. So even if the same data item is updated over and over again, it will end up in random locations and an adversary will not be able to correlate these accesses. However, randomization-based write-only ORAMs also tend to be very, very slow. The main performance bottleneck for randomization-based write-only ORAMs is the amount of random I/O that they need to perform in order to complete one access. Since data is placed at random locations on the disk, accessing a sequential chunk of data, for example, a file, requires a large number of disk seeks. Performing even a single disk seek on a hard disk is 10,000 times slower than the data transfer. On an SSD, the random placement of data increases wear and significantly reduces the lifetime of the SSD. But more importantly, random I/O interferes with important system-level optimizations such as file system caching, prefetching, etc., all of which implicitly assume that there is significant locality of access in the underlying layers. And without these optimizations, application throughputs are orders of magnitude slower. The research question that we ask in SqORAM is, can we build asymptotically efficient write-only ORAMs that also ensure locality of access? An indication that this is indeed possible was first provided by Roach et al. At CCS 2017. The observation underlying their work is that append logs also hide write access patterns. So if the data on disk was organized similar to a log-structured file system, then writes from a logical volume can always be performed to the head of the log. And this is going to hide write access patterns because the physical locations of the blocks are independent of their logical addresses. This also ensures locality preserving writes because no seeks need to be performed between consecutive writes similar to a log-structured file system. Unfortunately, this does not solve all the problems, since log-structured file systems are known to be very slow for reads. This is because the disk gets fragmented over time as files are updated and the updated blocks are written to the head of the log. Also, prioritizing write performance over reads by using a log-structured design does not make sense for all applications, since typical applications are read-intensive. So a typical file system workload consists of 60% reads and 40% writes. Therefore, optimizing reads can result in overall higher throughputs. So to address all these drawbacks, we introduce SqORAM. SqORAM is a new write-only ORAM that is locality optimized for both reads and writes. In SqORAM, we introduced a new locality preserving disk layout, where the layout of on-disk data closely resembles the data layout in the upper layer, example, the file system. So when SqORAM is used with a locality optimized file system in the overlying layer, then logically related data blocks are placed in proximity on the device. Further, to ensure that this layout is maintained throughout the lifetime of the device, despite updates to data, SqORAM also performs periodic reshuffles. The SqORAM layout looks like this. The disk is logically partitioned into buffers of exponentially increasing sizes. Each of these buffers can be considered to be an append log. The top level buffer has a capacity of 2 blocks, the next level has capacity of 4 blocks, and the last level has a capacity of holding all n blocks in the database. So in this way, the disk is actually partitioned into log n such buffers. SqORAM also has an in-memory write queue for performing operations that will be hidden from the adversary. So this is how a write is performed in SqORAM. Let's say you want to write 2 blocks of data received from the file system. First, you sort these blocks on their logical addresses, and then you write them to the top level buffer. Now notice that the physical location of the blocks are independent of their logical addresses because they're always written to the top level. Also, this mechanism ensures locality preserving writes, because when the write queue is flushed and blocks are written to the top level buffer, then no seeks are incurred between consecutive writes. Now let's say we want to write 2 more blocks of data. In this case, the blocks are going to be first added to the in-memory write queue. However, since the top level buffer is now full, we need to make space before the write queue can be flushed to the disk. For this, SqORAM employs level reshuffles. The way this works is we merge blocks in buffers at consecutive levels, and then we write these blocks to the buffer in the next empty level. So here, what we are going to do is first read the blocks sequentially from the top level buffer to the in-memory write queue. Then we sort the blocks on their logical addresses. And finally, we write these blocks to the buffer in the second level. At this point, the top level buffer is again empty and the writes can proceed. Note that during this process, we are still able to hide the write access patterns because the physical locations of the blocks in the new level are independent of their logical addresses. The blocks are also sorted in memory, which is not visible to the adversary. Storing the blocks sorted on their logical addresses has another benefit. We are able to ensure locality preserving reads when SqORAM is paired with a locality optimized file system. The reason for this is that a locality optimized file system usually assigns similar logical addresses to logically related items, for example, file blocks. Now, since blocks are stored sorted on their logical addresses, the blocks that are logically related will end up in close proximity to each other on the disk. Therefore, when logically related items are read together in a sequential chunk, for example, a file, then this access can be performed with minimum number of disk seeks. An important question here is how costly are these periodic reshuffles? Now, to estimate this, we measure the write complexity of this construction, which is the number of physical writes that you need to perform in order to complete one logical write. And in case of SqORAM, this is big O of log n amortized over all the writes, where n is the number of blocks in the database. Since we want to reduce the number of disk seeks, we also estimate the number of disk seeks that would be required on an average for these reshuffles. And this turns out to be 4 times log n by 2. And we refer to the paper for more details on how we come up with this expression. And we make an important observation here. The denominator in the expression for the number of disk seeks depends on the size of the write queue. And this can be amplified to reduce the number of disk seeks in SqORAM. So let's say we start with a write queue that has a capacity of log n blocks. Also, instead of the top level now having a capacity of only 2 blocks, it has a capacity of 2 buckets, where each of these buckets can hold up to beta blocks. In this case, we find that the write complexity of the construction still remains the same, which is big O of log n, amortized over the writes, where n is the number of blocks in the database. But the number of disk seeks is a constant when beta is equal to log n. So on an average, for the reshuffles, SqORAM only needs to perform a constant number of disk seeks. Now let's look at the procedure for reading blocks in SqORAM. For this, we need to first identify the buffer in which a block currently resides, and then we need to locate the block within that buffer. Since blocks in a buffer are sorted on their logical addresses, we can store a search index which will allow us to efficiently search for a particular block in a particular buffer. This search index can be implemented like a simple B tree. The read complexity of SqORAM in this case turns out to be big O of log n times big O of log n base k, where k is the fan out of the search index. Ideally, we want a lower read complexity, and so we introduce several optimizations. The first of these optimizations that we introduce in SqORAM is based on the idea that if we knew the exact buffer in which a block currently resides, then we can simply read the block from this buffer and eliminate searching in all the other levels. This is also not a privacy issue in SqORAM because we can reveal the location for reads, as SqORAM does not protect reads from the adversary. Also, since reshuffles in SqORAM are performed at deterministic intervals, the buffer in which a block currently resides in depends on its last access time. So the only thing we need to track is the last time that a block was accessed from SqORAM. And the way we do this is to store an additional data structure called an access time map, which tracks the last access times of all the logical blocks. The access time map is simply a B+ tree where all the pointers are replaced by access times. The root of the tree is stored at a fixed location on the disk, while the rest of the tree is stored within the ORAM so that it could be securely and obliviously updated. The way an access works now is first we look into the root and we find out the access times for its children nodes. Based on this, we retrieve the children nodes from the buffer in which they currently reside, and we repeat this process for all the internal nodes of the tree until we find the leaf where we find the last access time of the block that is required. Based on this, we can read the block from the exact buffer. Now with this optimization, the read complexity in SqORAM reduces to big O of log n base k times big O of log n base k, where one of these factors comes from the height of the access time map B+ tree, and the other is for the search index for a particular level. In practice, k can be very large. So with 4 kilobyte blocks and 8 byte access times, k is equal to 512. And for 1 terabyte database, log n base k is equal to 3. Further, SqORAM includes several other optimizations. This includes deamortizing the construction such that the worst case cost of the reshuffles is also the average cost of the reshuffles. And in this way, you do not have long wait times in between accesses. Also, we introduce some smart caching mechanisms to store frequently accessed parts of the maps in the memory. And in this way, you end up with almost constant read complexity when you're performing sequential accesses. I encourage you to take a look at the paper for more details on these. Now we talk about how SqORAM performs on real hardware and how it compares with previous work. SqORAM has been implemented both as a Linux kernel device mapper as well as a block device end user space. The main metric of our evaluation is throughput reported in megabytes per second. SqORAM maps data from a logical volume, which has been mounted with a 40 gigabyte ext4 file system, and the data is written to an off-the-shelf HDD. So based on the results in these plots, it's obvious that for sequential reads, SqORAM outperforms the previous state of the art, which is DET-ORAM. This is because SqORAM ensures locality preserving reads, which is not the case with DET-ORAM, which organizes data similar to a log structured file system. On the other hand, for sequential writes, DET-ORAM performs better than SqORAM because the overall asymptotic complexity of writes in DET-ORAM is lower than SqORAM. Random reads and random writes also follow similar trends. More importantly, we also performed application benchmarks. In this case, again, data was mapped from a logical volume to an off-the-shelf HDD, and the logical volume was mounted with a 40 gigabyte file system. We ran application workloads on top of this file system. The specific applications that we considered are a file backup server, which has a read-write split of 30/70. So this is a write-intensive application. The other two applications we considered are read-intensive. So you have a typical file system workload, which has a 60/40 read-write split, and a video server application, which has a 70/30 read-write split. Now, as expected, DET-ORAM outperforms SqORAM for the backup server, since it is a more write-intensive application, and DET-ORAM is more optimized for writes. But for the file system workload and the video server workload, SqORAM outperforms DET-ORAM due to locality preserving reads. And in fact, for the video server case, SqORAM is only 50% slower than the baseline. So in conclusion, this work introduces an efficient write-only ORAM construction that ensures locality of access for both reads and writes. In SqORAM, we are able to do this because of a new locality preserving disk layout, which ensures that the layout of data on disk closely resembles the layout of data in a locality optimized file system. And as a result, we are able to achieve near optimal throughputs for typical read intensive applications on off the shelf hardware. Thank you. That's all I have. And I will be very happy to answer questions in the Q&A session.